new standards.
Oh yeah.
This class we are officially going over the new standards.
Does that mean we're gonna do the first lesson again to report it?
No, I posted the I posted the notes with all my writing on it. I figured that'll do. Yes, Francesca. Yes, you can scan, show, and go. Are you able to do that? Okay.
But I guess since it's already broken, it gets broken super easily. So it keeps on getting broken all the time.
But that research is actually really interesting.
Yeah, I think
and
I'm looking
stuff
to that.
that
Looks
could
so cool.
be actually useful. So
That's the kind of stuff that I'm like really, that makes me really interested in chemistry, like the way that you can. And I low-key have thought that. Oh, I've like wondered if that was possible before, and now I see that like it
I
actually
can
happens.
investigate further. That's my goal, is to get you all to like think beyond just the curriculum and this connection. All right, so let's go ahead and get started. Unit 3, lesson 2. I told you there's only 5 lessons this unit. We will be having 2 labs. One of them will be the one we do next week with the starch iodine titration, which is a redox titration. That's why we're doing that lab. And then the other lab that we're going to do is we're going to do electrolysis. We're going to split water, basically. We're going to perform electrolysis, and we're going to build something called a voltaic cell, which means we're going to be turning chemical energy into electrical energy. And so that's going to be coming in a couple of weeks. I have ordered materials that are on their way in for that second lab. The starch iodine, I'm ready for that one. But the second lab, I'm having additional materials come in to the school that we'll be using for that in a couple of weeks. When I have the exact date nailed down, I'll let you know. And you're definitely going to have your Unit 3 exam before Thanksgiving break. Like I said, there's only 5 lessons in this unit. So you can expect to have most likely the week before Thanksgiving break. But when we get close to it, I'll let you know. So with that being said, let's go ahead and get started with redox part 3. So last class was technically just a review of what we had done before. And so everything from now on, let me just make sure I'm recording, is the new content for the A level. And so the first learning objective we have today is to predict the identities of substances liberated during electrolysis from the state of the electrolyte, molten or aqueous, position in the redox series, which we will learn later is called the redox potential. For now, we're just going to reference back to something we used to call the metal activity series back in pre-ACE. Do you remember that thing?
Are we supposed to remember that?
You can look at the face I gave you, and that'll give you the answer. And the concentration. And so we'll be looking at that today. And then the second objective is to calculate the quantity of charge. That's a math question, right? The quantity of charge passed through during an electrolysis. This is called the, and I swear this is the formula. It's the QUIT formula. QIT.
It's very important.
Here's the one we do next class. It's called the FLEE formula.
We
I always find that to be hilarious. That the,
exactly.
I didn't choose those letters. Those are the letters in the standard.
I think it's trying to tell us something.
You'll find out next class. It's the QUIT formula.
Is that the same as the one you
What Q is? Oh no, it's not QSP. No, because there's no SP down there. It's not an equilibrium constant. We're now talking about electricity. So this is charge. So the mass or volume of a substance that's liberated. What does the word liberated mean?
Like really.
Release. So it's the Cambridge word for this went out. What went out during the process of electrolysis. So I'm going to teach you what is electrolysis. If you don't know what it is, we're going to go over what exactly that process is. And then we only have 2 standards today. And I think I told you that we may not get through all of this today. So we're going to, like I said, whatever we don't finish today, we're going to do on Monday. But all of this along with the FLEE formula is the stuff from lesson 2. So there's 5 total lessons in the unit. It's not that many. So I have the luxury of time to go over what needs to be went over so that we have a full understanding. All right, so before we get to the objectives, we had a slide from last class we didn't do. Do you remember? We didn't do this redox titration question. I thought your brains were a little bit mush at the end, and I was like, okay, we'll just save this for later. This is actually an example of something close to the titration that you're going to do next week on Wednesday, because you're doing something called a starch iodine titration. And so here they tell you have a piece of copper alloy. What does alloy mean?
Like it makes a metal.
It's not just copper. It's copper and other metals. So it's a copper-containing alloy, and the alloy has a mass of 0.567 grams. We dissolve it in acid.
5, 6, 7.
It is dissolved in an acid, giving 100 centimeters cubed of a pretty blue solution, which all the copper is present as copper 2+ ions. Copper in 2+ form in water, copper hydrated is blue. So then an excess of potassium iodide is added to a 25 centimeter cube sample of this solution. So an excess of Ki. All of the copper is precipitated as white copper iodide. So they took it all out, they precipitated it, and it's a white solid. Interesting. Copper 2+ ions are the only component in the solution that react with Ki. This is reaction 1. Then the iodine that's released, which, like I said, this is actually going to be similar to the lab you do next week. You're going to create iodine, and then you're going to titrate it with sulfur oxide. It's actually sodium thiosulfate is what you'll be using. And this is reaction 2, and you get these products. And then they tell you this titration right here requires 20.1 centimeters cubed of a 0.02 mole thiosulfate to reach the endpoint. Can we calculate the moles of I2 for the titration in this part? What would we do? I want to get us as comfortable with titration math as possible because the most common math you're going to see on paper 5, right? So what would we do, Caesar?
Yes, it moles of sodium sulfate.
Yes. So how would we get that if we've got the volume and the concentration? So it's concentration equal mole over dm cubed. That formula over and over and over again. So it's actually multiply both sides by dm cubed, and it's always dm cubed multiplied by concentration in the mole. So what I did is I was like, okay, 0.02010 times 0.02, and what does that give me? I get 4.02 times 10 to the negative 4. Let me know if you get the same. That's not the answer, though. What is that?
That's moles of S2.
Moles of S2O32 minus. Now what do we do? Divide by 2. Because the geometry says, well, there's 2 of these for 1 of those. So that means I must have half the amount of I2. And so then the second part, I'll just write it over here, is 4.02 times 10 to the negative 4 moles of S2O32 minus. As long as you remember to divide by 2, they give you the point. But the correct work for that is to show the 2 S2O3s on the bottom for 1 I2 on the top. And so your answer would be 2.01 times 10 to the negative 4. Okay, so that's my I2. So then how would I find the number of moles of copper? What I do? We took the iodine here. So we're thinking backwards. We took the iodine, and that was a product of the reaction of copper and I minus, right? So what they're asking us to figure out is how much copper, and how much copper in the original solution do we have? So the first thing we need to do is go from the iodine we just created back, so we're thinking backwards, back to the amount of copper that reacted with it. So what would we need to do for that? If I've got 2.01 times 10 to the negative 4 moles of iodine, what comes next? How do I get to copper? Yep. That gives you the amount in the titration. So 1 mole I2 is for 2 moles Cu2 plus, and that right now would give me, I did something else immediately, so I didn't break it step by step in my own work. But that gets us, I think, back to 4.02 times 10 to the negative 4, if I'm not wrong. But that's the moles of Cu2 plus and how much Cu2 plus solution. if you read the work, what does it say? How much CO2 plus reacted to make this iodine? Does it say a volume there? 25. The Ki is added to 25 centimeters cubed, right? So then
I misbelieve.
this is 25, but you had 100 of the solution that you had dissolved the copper in. So if this is the amount of moles in 25 centimeters cubed, how would you find the amount of moles that was in the original solution? What would you do? This is the amount of moles that reacted here, which was 25 centimeters cubed reacted, right? So we have the moles in 25 centimeters cubed, but technically the original alloy was dissolved in 100 centimeters cubed. Does anybody have an idea of what we could do here?
That's the M1.
Multiply by 4. Multiply by 4. Because we want to know how much is in 100 centimeters cubed. And so basically it's 4 times the amount, right? So if I have 4 times the amount of original solution, I'm only using 1/4 of it. That means I must have 4 times the amount of moles. So multiply by 4. And the way that they'll show this in the mark scheme, just so you have an idea of how they show it in the mark scheme, is they would do 2.01 times 10 to the negative 4 times. And then it was, like I said before, 1 mole I2 over 2 mole Cu2 plus. And then see if this makes sense. 25 centimeter cubed, 100 centimeter cubed. That makes sense. Because this is how much I had, I need to get rid of it. And this is the amount that I want, the amount in 100 centimeters cubed. So I put the amount that I had on the bottom and the amount that I want on the top. It's the same concept. The final answer here is 0.00168. 1608. So that's the mole of copper in the alloy. So then how do I get to the percentage of copper in the alloy? I've got the moles. Isa?
You have to find the moles.
I have to get grams and compare. So this would be moles of copper to grams of copper, which means do what? Take your moles and multiply by the molar mass, which is 63.5, which then got me to 0.102. Let me know if you get the same. I did check the final answer in the mark scheme, but let me know if you get the same number. That's not the final answer. I got 0.102 grams of copper. That's how much is in the alloy. But the whole alloy is 0.467. So how do I get the percent of copper in the alloy? That divided by the whole thing, which is 0.567 times 100. And the final answer was 18%, which they already put the percent sign in there. You have, and I did the homework for this too. It was in the first homework. You have 4 titration math questions in the homework. It says in the homework, because I wrote it over the summer originally, to wait until after the titration lab to do it. Disregard that. There's only one question that you would need to know from the lab, but I'm telling it to you now. In one of the homework questions, they ask what is the indicator used in an iodine titration. Does anybody know what indicator is used in an iodine titration?
Oh, it's like CH2, right? Something like that.
I mentioned it. How do we know in qualitative analysis if we have iodine? What do we use?
CH2.
What reveals the iodine? It's not actually talked about here. What reveals the iodine? We used it in several qualitative labs last year. It didn't show up on the exam. It was in the dropper, yes. It was really gloopy.
Oh, starch.
It was starch. So the indicator, and yes, I have to make it for next Wednesday's lab. The indicator for iodine is starch. It'll change I- into I2, and you'll get that black looking gloopy solution. Which is why I said it's going to be a little Halloween in the color scheme, because you're going to make a black solution at one point in your titration. Yes.
I'm sorry. Why couldn't know this is there?
Silver nitrate? Why would you use silver? Like you would want to precipitate silver iodide here. It's not pure iodine. So it's not going to do the thing you want it to do here. Because if it's silver iodide that's coming out here, then you have AgI minus. And this is a redox to change iodine to iodine minus. If it's already I minus, that's not going to be a good, like that's not going to work. The proposal won't work is the idea because that's not redox. Answer your question? Yep. All right. So
Red cat.
here we go. That was still a review. Crazy. So now we're getting into the new material. So what we're going to do is define electrolysis. And then should we have the time, I hope we do, we'll at least get started with the math today that you're going to need to know. But first, what is electrolysis? And so for me, this is one of the more exciting topics in A-level chemistry because it's electricity. And so for those of you who like physics or think you might like physics, this is getting closer into what you would study in a physics class because remember, chemistry is the middle ground. You see some biology in chemistry and you see some physics in chemistry and how it all applies to materials. So this is really called at a more advanced level studying material science. That's what we study. But which is why chemistry is defined as the study of matter, materials, and then changes it undergoes. So electro means electricity or electrons, right? And then lysis is a word that you would have heard from biology, should you remember. Does anybody know what lysis is? And you heard it in hydrolysis in chemistry. What does lysis? Lysis means break apart. So if I break down the words prefixes and suffixes, right? It tells us hydrolysis is break apart with water. This is break apart with electricity. And so basically we go, we apply a battery and we're going to break apart elements. So electrolysis is the decomposition of a compound. So like an elemental decomposition that we talked about all the way back in pre-ACE. Remember in pre-ACE chemistry when we were like, yeah, we could just like do this thing. And I'm going to use magnesium bromide because Lisa brought it up earlier. We could totally do this thing and then we get this and that. Remember that? Well, we're going to talk about how in the world does this happen today because that's actually not natural. That's not normal. Why is that not normal? So, in order to make it happen, we have to apply an electric current. Like I said, you have to electrocute. You have to electrocute the salt. You have to apply electrical current to the salt to get it to break apart. And so, this method is used commonly if you need to extract a metal that is high on the metal activity series out of a compound. Metals like sodium that don't exist naturally by themselves, but yet I have some. How did we get there? They use the method of electrolysis. And so why is this weird? Why is this decomposition weird? And I don't think any of y'all questioned me back in pre-ACE, but technically this shouldn't make sense. This is not that's not normal. Why not? Yeah, you're decreasing entropy. Okay, that's one reason that doesn't seem like it should work. What else?
That looks like a reverse entropy formation.
So what would be more natural? The magnesium in the form that it's like its noble gas, or the magnesium in its standard form? What's more favorable? Be like the noble gas, right? We said that all the way back in intro chemistry, that elements gain or lose electrons. They form compounds to be like their nearest noble gas because they will be more stable, right? So this technically should be the more stable form of magnesium with bromide than magnesium and bromide separated. So we're going from something that's more stable to something that's less stable, something that's less favorable to occur. That's why you have to electrocute it. That's why you have to force that thing to happen. Because what are we actually doing here if you think about it? You're taking magnesium, which has a +2 charge. It's lost its 2 electrons, and you're saying, I'm giving those back to you. Right? That's literally what you're doing here at the atomic level. You're like, well, you were stable like a noble gas, but I'm giving you back those 2 electrons. And bromine, you know, you were stable like your noble gas, and I'm taking that electron away from you. Not normal. Do you agree with me? That's why you haven't, at this point, like in AS chemistry, you never really saw an elemental decomposition. You only saw a thermal decomposition in practice. Because elemental decompositions are not normal, even though I teach them in pre-ACE just to get the idea of what's happening. Yes? No, because I don't want it to be. We'll discuss aqueous versus liquid. If you go back to the standard here, it says that your electrolyte, which I still have to define to you what that is, will either be molten, which is liquid, or aqueous, which is AQ. But if it's aqueous, we add in some additional complications into the mix. Because now H plus ions are there and OH minus ions are there, and we have to talk about that, and we have to talk about that today. So it's a little more complicated, but not overbearingly so. We'll get to it. That's why I said we're going to be a long time in these objectives. Because I first have to define what everything is, then we have to go through the processes. So we have an idea now. This is the concept. We're going to take an ionic compound and we're going to split it apart into its elements. Okay, so electrolyte. That's the ionic compound or whatever compound we're trying to decompose. So it could be an ionic compound or it could be an acid or a base. So this is going to be an ionic compound, an acid, or a base, which is also an ionic compound. So I don't know why I would need to restate it, but I do. Why would those be electrolytes? What is an electrolyte? I know in your class, I had went over it in pre-ACE, but that word has not been discussed again since pre-ACE chemistry, unless you were in the Olympiad review. We mentioned it there. What's an electrolyte? It's something that, Francesca.
It's attracted to negatives or like electrons.
It's a substance that conducts electricity. So it has some kind of charge carrier in it.
Electrolyte.
What?
Electrolyte.
Technically. So I don't want to say the experiment you do to test this, so I'm not going to. But I did have students that have tested it before that were like physics kids that would test that. But yes, you have plenty of electrolytes in you because when you sweat, what is sweat but water and salt? What is salt but plus and minus charges? Doesn't that carry charge? Okay, so electrolyte is something that carries electrical charge. And so it's an ionic compound because an ionic compound has the plus and minus charges, right? M plus, X minus. Acids and bases also have plus and minus charges because you've got the H plus in acid, right? So in acid, you've got H plus and X minus. So you've got these ions that are, if it's aqueous, running around your solution carrying charge. And if it's molten, they're also moving around carrying charge. Notice, ionic compounds have to be molten or aqueous. What does that mean? If it's NaCl molten, that means what about its ions? Correct. So ions can move. That means that its three-dimensional lattice has been broken apart. The three-dimensional giant ionic lattice that it exists as, like the ones that AS chemistry made up there, they have one up there, it breaks apart so that the ions can move. And then NaClAq would be also the ions can move through water, right? So these are both situations where the ions can move. And so what about NaCl solid? Could that be an electrolyte? No. Because it's stuck. Your ions are stuck in the three-dimensional network, right? They're stuck like this. and they don't move. Remember, solids only vibrate, they don't actually move around, right? Solid phase ions don't move. When we did the screaming gummy bear, I had to melt the potassium chloride. Why did I have to melt it? Go ahead. Because the ions aren't moving and it doesn't have near enough energy as a solid. If I sat and threw a gummy bear into a pile of solid potassium chloride, it would just be a nice little, fluffy blanket for it. Like, it would be laying on it, it would be doing nothing. It had to be hot enough, it had to be moving, and then you could get your effective collisions out of it to, get a very interesting response out of the gummy bear.
Interesting.
Yes, interesting. So that's the electrolyte. That's what an electrolyte is. It's an ionic compound, an acid or base, got to have a charge carrier for you to have something called an electrolyte. It's technically the compound you're trying to split. The electrolyte is the compound that you're trying to split apart. The next thing is, what is an electrode? So an electrode is either a pure metal or graphite. Some kind of solid surface that allows for the conducting of electricity. If you remember back in pre-ACE, for those of you who had pre-ACE, we did a lab actually around this time of year where we put electrodes, they were copper electrodes, into different solutions, and we saw a little meter go up and see how much electricity the solution conducted. And some of you would put the electrodes in like a solid and be like, "Miss, is that doing anything?" And I was like, "That's the whole." When you put the electrodes in the solid, it doesn't do anything. You will be working with electrodes again very shortly in the second lab that we do, because we'll be building two types of cells. We'll be doing this type of reaction, which is the forcing the reaction to happen with electricity. And then we'll be doing the second type, which we'll learn about next week, starting later next week, on how chemical energy is converted into electrical energy. And so electrodes, these are going to be, and they're in here, this is the cell, these are the rods, these are the electrodes. They're either made of one of the metals that you're using in that solution. It would need to be a metal that's low on the activity series so it doesn't react. And it could be graphite, and we'll ask why graphite in a little while. Anode is the next term you need to be aware of. An anode is the identity of the positive electrode. The electrode that is positively charged is the anode. So that's why you see this little positive here where the anode is. It means this is positively charged. And the cathode is the negative electrode. Like that. So this is a source of the negative charge. So the way that electrons move through, and this right here, this is a wire. That's a wire. And the electrons would be moving from area of low concentration to area of high concentration. So the electrons are moving like this through the wires. And here is where we would typically have our battery. I have to see how many batteries I have. I'll have to purchase some 9-volt batteries for us. And we'll be attaching our little electrodes to a battery to basically force this to occur. Yes. So next thing is your power source is supposed to be direct current, not alternating current. Not a physics teacher, can't really talk too much additional about that, but it does need to be a direct current source, not like a changing current. That's what alternating current is. So it needs to be like same amount of current going through. All right, so electrolytic cell, this is just a little bit more information about it. Notice that, and I think I brought it up here. This is negatively charged and this is positively charged. So if I have two ions in the solution, Na plus and Cl minus, where would the Na plus be attracted to? The cathode or the anode? The cathode. So cations are attracted to the cathode, and that's where it gets that name. Cations are attracted to the cathode. cations are positively charged. This is back to that thing back in previous chemistry I told you in Unit 1 that if you don't understand this, life is going to be terrible for you for both chemistry and physics for the rest of your life. How charges work, right? So positives are going to be attracted to negatives, opposite charges attract. So the idea is that if I have a cation which is positively charged, it's going to be attracted to the negatively charged electron. Guess what that negatively charged electron has? Why does it have a negative charge? It has a bunch of electrons. And so what does it do? It gives those electrons to, in this case, sodium, right? And it changes sodium from sodium plus to sodium solid. Could that happen in water?
Yep.
Could it? A question to continue in a little while. We'll continue on that question. But this notice here is molten. Molten means no water. That is just liquid NaCl. So the Na plus is gaining an electron, and the Cl minus is losing an electron. So technically, what are you doing in this reaction? You're making sodium solid, which we know is highly explosive because it don't want to be that way. It's not gonna have no water. I tested it. It doesn't happen. You'll test it in a couple weeks. It's still not gonna happen.
Well, if that doesn't happen, we have chlorine testing.
Oh, we're not doing the chloric gas thing. Although we can talk about it. You can actually make small amounts and I'll explain the reason why, but it has to be a very low concentration. Cl minus goes to Cl2. What is happening here? You're going from Cl minus, not dangerous, to chlorine gas. So this is one way in which chlorine gas can be produced. We don't want to produce chlorine gas. It's a very toxic substance.
What does it taste like?
I don't know. And I don't want to know. All right, so this is just basically summarizing some of the things I already said. Electrons should be moving from the anode to the cathode. So that's actually important to note. Electrons move from the anode to the cathode. So this is where you have all your electrons at the cathode. That's where you have a great density of electrons. And then at the anode, the electrons are being pulled away. If that makes sense. So this will have the positive charge and this will have the negative charge. And one of the things you're going to have to remember is that electrons always flow from anode to cathode. That's the direction of electron flow, no matter what cell you look at. So on the next slide, ink, y'all, is too expensive, so I did not print this out in color. It is way too. I'm not kidding. We just spent $400 in ink in my house.
Per milliliter, a printer ink costs more than human blood. Money.
I would.
Like that's insane.
I think that's.
It is.
The amount of
and it's
printer ink.
like
I think that's a true statement based on how much money we just had to spend to have just a little bit of color ink in our house.
It's probably like a factor of 100.
So Miss Lee, don't have that much money. We're gonna, so you're gonna have to fill in the colors yourself. But there's a way to remember what's happening at the cathode and to remember what's
I already
happening at
colored
the
it.
anode. And it's this little, mnemonic device. Red cat. So what does that mean? The cathode is where reduction happens. So cathode is reduction. The red cat is the way to remember it. Cathode is reduction. This is, for example, in that example that we just saw, where you would have this happen. Right? Okay, so what about the anode? The anode is where? Is where oxidation takes place. And that's the way to remember it in this class and any future class that you take. Where whatever is your anode, that's where your oxidation is going to take place. So an ox is the way to remember it. And so looking at the one that I just showed you, if I had Cl minus, it would go to Cl2 gas plus E minus, releasing an electron, oxidation definitely taking place. And so this is a way to help you remember what's going on. Reduction happens at the cathode. Oxidation happens at the anode. Bless you.
Thanks.
Do you think you're gonna have to develop half reactions, which I talked to you about last class shortly? Absolutely. That's what we're gonna have to be doing. So that's where this is moving. That's why we're moving slowly. We have to time, but I want to make sure you have a full understanding of what's going on because some of these concepts are brand new. And the last time we even talked about the word electrolyte was 2 years ago. So it's been a long time. Yes, that's all.
So we're gonna get like those humongous equations and like, or is it compress them to the half equations?
We'll see. You'll see. It's not going to be terrible. You'll see shortly. All right. First checkup from the textbook. Why does an ionic compound have to be molten to undergo electrolysis? I kind of already asked this, but let's go ahead and write down the reason. The ions have to be free to. Ions must be free to move. If they're in the solid state, it's not going to happen. The ions are not going to move. You can test again. I'll give it to you when we do the lab a couple weeks from now. You could put those electrodes in a solid and you'll be like, nothing's happening. And I'm gonna be like, yes, nothing's happening. That's right. I'm gonna do it in a 3 days class in a couple weeks, I'm sure. Like probably 3 weeks from now, and they're gonna be like, Miss, nothing's happening. And I'm like, yeah, that was the intention.
Miss, why is
They're
your
like, this is boring. I'm like, yep, that's boring. I agree.
calculator has a headphone jack?
I don't know why the calculator has a headphone thing. This is just my favorite calculator. My favorite calculator. Had it for like a decade.
They probably have
Calculator with a
access to
headphone thing?
All right. Give 2 properties of graphite that makes it a suitable material for an electrode and explain your answers. We won't go too deep, but I think it's a good analysis question. What are 2 properties of graphite? Just to remind you, this is its structure. Why would that be? Yes. So number 1, delocalized electrons.
I forgot about that.
So delocalized electrons, because some of these are sp2 hybridized and some of these carbons are sp3 hybridized. And the sp2 hybridized carbons have an open spot. They have an open spot, meaning they're not bonded, meaning that they have electrons that technically are free to move in between the layers, right? So delocalized electrons, and the reason I said this allows for electric current to pass through the material. You have to have electrons free to move. So although the ions are moving, there are no ions in graphite. There are delocalized electrons, much like a metal, which is why we can replace a metal with graphite. And often graphite is a superior material to use. Why is graphite a superior material to use? What do you think?
Doesn't have like
So it's giant molecular, which means it has a super high melting point, right? So you could put it with a molten substance and it will still work because it won't melt yet. So that's one excellent reason. Why else?
Why doesn't have like the plus on
Cheap. Carbon is cheap. Graphite is cheap. It's a cheap material. Like the other main metal that we use that you're going to see is platinum. Platinum's not cheap. Platinum's very expensive. Graphite is cheap. I'm ordering graphite. It was like $3 a rod. It's coming in the mail.
We have platinum.
No, I don't have platinum. We don't have that kind of money.
How much does
And I don't know if I write a grant if that would get approved.
How much does a rod of platinum cost?
How much does what?
Like a rod of platinum.
Go ahead. You can look that one up. I'm pretty sure it's probably more than I make in like a paycheck.
Yes, I'll just give you my calculator to convert it.
You can harness the tiny amount of platinum out of these platinum.
It's $50 a gram.
Okay.
Just for a gram.
1 gram. For context, the amount of magnesium sulfate I had Stefan and Sophia put into the little things for free was 2 grams each. So that would be equivalent to for each person $100.
I guess I'm
It's not that bad. All right, so that was reason one, that it's a great material for an electrode. It's basically it has the localized electrons. What's a second property, physical property, or just property of this material that you think would make it a great conductor of electricity? Anybody got another idea? Caesar said the localized electrons.
High melting point.
Yes, high melting point. So high melting point. And this is due to the giant molecular structure. It can withstand molten metals. So high melting point can withstand very high temperatures.
The would you easily contaminate the solution because like it rubs off easily?
Which is why platinum is often used, because it doesn't.
You see, you don't.
So cheap though. All right, so I also have a third reason. You don't have to write it down, but the fact that it's arranged in layers makes there a pretty easy pathway for the electrons to move through in between. So it allows for a steady current of electricity. That also is the same idea of the molecular or the metal organic frameworks, that those spots in the middle is a good place for electricity to go through. So that helps with their properties. So I thought that that was interesting because it kind of tied into this. All right, so let's take a look at our next question. So our next question is talking about equations. Yay, chemistry, all about equations. When lead iodide, PbI2, we actually make that freease. When we do the chemical reactions lab, and I tell you, please, for the love of everything sacred, don't throw that down the sink because our poor fishies. So when lead, it's a very yellow, very golden. Some people call it the golden rain reaction. When you produce lead iodide, because it's very pretty. When it falls down, it looks like sparkly, like gold, but it is yellow. No, that's called brain damage.
Well,
It tastes like brain damage.
I know lead acetate is sweet.
How do you? Okay, never mind. So when lead iodide is electrolyzed, the following reactions occur. You get this half reaction and this half reaction. Which one of these happens at the cathode? So what happens at the cathode? Remember, red cat, right? So then which of these is the reduction? Francesca.
No.
Ramon.
Yeah, lead.
Lead. So this one. That happens at the cathode. That's correct. What's the oxidation number change for each iodide ion? Is the second question here. What is the oxidation number change of each iodide? It goes from -1 to what number? 0. So the oxidation number changes +1. It goes up by 1. Increases by 1, you could also say. All right, so that's some standard, just textbook questions. We haven't seen anything out of paper 4 yet. We're still like, this is actually pre-ACE.
No, we did put paper.
If I had the time to cover electrochemistry and pre-ACE, this is what a question might look like. What equation represents the reaction at the cathode?
Cathode is red
It
cat.
is A.
Yes. Red cat.
And this is a process called electroplating, where you use electrolysis to, for example, plate a pan. So when they make like the pots and pans that you used for cooking, electroplating is a process to get a specific metal on the top of that pan. It's called electroplating and uses electrolysis. All right, so this is also pre-ACE. This is also pre-ACE, believe it or not. It's not on the AS multiple choice. It would be in the pre-ACE. But we didn't go over electrolysis in pre-ACE. Which row describes the electrolysis of molten potassium bromide? So how would we think about this? Like, what thought process would we go through? First thing to do is what? What's happening?
We're breaking it down.
What am I doing with this? I'm going to take this and I'm going to split it apart. When we talk about electrolysis, which we're literally doing is we're taking the elements and we're breaking them apart into their standard state, which is the decomposition. So we first have to do the decomposition. So what would this decomposition be? The elemental decomposition, what would you get out of this?
K plus.
K, not plus.
Solid.
It would be K in its standard state, right? So K solid. And then what would my other product be? Br2 liquid. Remember, the products of elemental decomposition are the elements in their standard state. So just to remind you, when I make my products for decomposition and elemental decomposition, if I'm decomposing a compound, I'm going to elements in their standard state. We went over saying that's not natural. That's why we have to apply electricity to make it happen. So then, this is actually two half reactions, isn't it? And we learned how to break that up last class. What would the two half reactions be here? K? No. K plus 1, right? Goes to K. And which side would the electron go on? Do we agree? That's one half reaction. What's the other half reaction? Br minus goes to 1/2 Br2. I got that. 1/2 Br2. And what side does the electron go on? Here it's on the right side. Okay. What does the anode mean? Which process is taking place at the anode? So an-ox, right? And red cat. So which one of these is the oxidation? Bromine. Because you go from -1 to 0, just looking at the oxidation numbers, or looking at the electrons released, right? That's oxidation. So your product at the anode is bromine. Cathode, what's my product? Potassium. Because it goes from K plus to K. Start to go down. So the answer here is B. For those of you that, yes, Caesar.
Can you think about it like anode minus and then like Br minus and go like 2 and 2 together?
So you could think about it that the anions are attracted to the anode and the cations are attracted to the cathode. So here's where I'm going to scare you. When we get to the other type of cell, the chemical energy cell, the processes are exactly the opposite. Because instead of applying electricity to force something to happen, in the second situation, the reaction happens the way it's supposed to naturally. And chemical energy is converted into electrical energy, which means that the charges flip. So therefore, although you may use that right now, sure,
You can later.
be careful later on.
So where
I said it, I think to Priya, I was like, this is chemistry without exceptions, like right there. And then if you include all the exceptions, it's like that.
No, I think it'd be a singular shape.
Yes.
Red eye.
I'm sorry? Contact? No, I'm so sorry. I don't wear contacts. Uh-oh. All right. Continue? Are we good with this? Can you imagine doing that in Prius with oxidation? Do you know how overwhelming that topic was already for students? Because we had to complete and balance all the different types of reactions, balance equations, learn redox. Imagine adding this in too. It's too much. Because you barely know how to make equations to get to what the concept is here, which is why I saved this one for later. I'm like, it's fine. All right, so how does electrolysis work? I've mentioned it before, but this is definitely important. In electrolysis and in all cells, the electrons are always actually going to move from the anode to the cathode. Because they're going to move from where oxidation takes place, that means electrons leaving, to where reduction is taking place, which electrons are going there, right? So half reaction, cations will always gain electrons to go back to their metal solid, and then the anion will lose electrons. So the next topic you're so very excited for. We've now defined what is an anode and a cathode. We've looked at how to identify the anode and the cathode. We still haven't done anything in paper 4 yet, great? We've literally just done definitions. So the next topic is, what if we had an aqueous solution? And let's revisit something called the metal activity series, back from pre-ACE. So back in pre-ACE chemistry, when we first learned single replacement reactions, I gave you a chart. It looked a little like this. This wasn't the full chart. The chart is larger. I pulled this from a Cambridge resource. So this is like an abbreviated version of the chart. Because it does not include everything. Not nearly everything. There's another chart on your notes from last class that has more metals on it, if you want to look at a larger one, but I wanted to save slides and not reprint it, so I didn't, because I don't need it for these examples. But how does this work? The metals that are at the top are the most reactive. And we said that they're the most powerful, which means what?
They take the place of the
If I have a single replacement reaction, right, and I've got that metal, so if I've got the metal plus I've got, you know, XY, if this metal is more powerful, right, on the series, that really just means it wants to lose its electron more. It's like, hey, you, I'm gonna take your spot. Goodbye, right? And it's gonna kick out the other metal and take its place with the non-metal. That's how signal replacement works. And so that'll only happen if the metal is more reactive. And so taking a look at this, can you predict if these reactions will happen or not? And what would be the product if it does? The first one, will calcium kick sodium out of the compound? No. Calcium's like, hey, I'm gonna take your spot. And sodium's like, no, I'm gonna keep this spot. Because sodium is more powerful than calcium, right? And if you did complete balance that reaction, you'd be telling me something crazy. So the answer is no reaction. But if you messed up and you said that this was the product, you would be telling me the following. What would you be telling me if you said this reaction happened? You would be telling me that in water, we are producing pure sodium. Don't think so.
We have to memorize the chart thing.
You have to memorize it?
Give me a minute to finish this. Yes.
So remember if we put potassium in water, inside water?
If I put potassium in water, so I'm thinking I want to use some of our science lab fees if they have it available to purchase some potassium, because that's just an awesome reaction to see. It's explosive.
Wait, what?
And it explodes with purple flame.
Don't let the ceiling on fire.
What?
Don't let the ceiling on fire. It's not.
Oh, yeah. I lit the ceiling on fire the other day. It's okay. Everything's fine.
See me once
I
saying
think the floor is burned too. If you look back there, pretty sure I burned the floor. There's like fire all on the floor.
Where?
You know, it's fire resistant-ish.
When did that happen?
In pre-ACE last week, yes.
If I recall, wasn't what's it called? The ceiling lights once damaged, or because of the
Probably.
sodium reaction?
Not because, no, it wasn't because of the sodium reaction. But we've had our lights flicker on and off sometimes and can be replaced. We haven't gotten our new ceiling lights yet.
I know.
Oh,
we're
we're
getting
getting
it perfect.
We're getting
They're
the ceiling lights?
changing all the lights in the school. Like the other light. I like this light.
Wait, what other
If
light?
they go to the brighter light, that's probably gonna give me more headaches, so it's not a fan. But whatever. Does this happen? Does this happen?
Yes.
Well cooked. Yeah.
Yes, this happened. So what will my product be?
I like it when it doesn't happen. Let's see.
So you basically get copper out of this, right? And we did this when we did single replacement reactions. We did a bunch of practice ones and we just basically saw did they happen. And if they didn't happen, it was really boring. And you're like, this was boring. And I'm like, yep, it didn't happen. And then this final one will zinc pick out sodium. Zinc's like approaching, like, can I kick you out? No, zinc's way lower than sodium, right? So zinc will not pick out sodium and you're going to get another no reaction. So this is what we did back in pre-ACE. And then, so here's how it goes at the negative electrode, which is where your metal is going to approach. So here you've got your cation, right? And you want to see if you're able to reduce it like this. So at the negative electrode. If you've got an aqueous solution, you both have metal ions in that solution and you have hydrogen ions if it's water. And when you apply electricity to the solution, you have to decide whether you're going to get the metal or you're going to get hydrogen that gets reduced. One of those two ions are getting reduced because they're both present in the solution, in the aqueous solution, either the metal or the hydrogen. And so you would look to the position of the metal in the reactivity series. If it's above or below hydrogen. If the metal is above hydrogen, then hydrogen gets reduced. And if the metal you have is below hydrogen, then the metal gets reduced. So what you're going to notice here is the following. In most situations, in aqueous solutions, the metal's not getting reduced. It's actually hydrogen that's getting reduced to becoming hydrogen gas. Except if you have copper, silver, or gold. Just throwing that out. So what would you have to know? Somebody asked, do I have to memorize the series? You have to memorize whether the metal is going to get reduced or if hydrogen is going to get reduced. That's what you have to know. And platinum would also be below. As I said, this is kind of an abbreviated list. I picked this up. There's a more full one that I printed last class, but I don't have it on the slide to save space. But there's a larger one. You can look up larger ones. But this is the one from Cambridge, so I figured it was a good summary of a lot of the common ones you're going to be asked. But you can draw some conclusions yourself. There's very few metals that are less reactive than hydrogen, copper, silver, and gold. And if they're more reactive than hydrogen, which is most of them, then they're not getting reduced. It's hydrogen that's getting reduced. So all your group 1 metals, all your group 2 metals, and then a lot of your transition metals even, hydrogen's getting reduced instead. So I would just remember the ones that get reduced actually, which to me is copper and silver are the most common ones. Yes, add some.
What about when it is hydrogen?
Oh, we'll talk about that. It's coming. There's a blank slide here for a reason. All right. So, and that'll probably be the last thing that we do given the time. I told you this was going to take a while to get there. There's a lot here, which is why the only homework that's due on Monday is the one from the first lesson. And then the one from today, I put it up, but it's not going to be due till later next week because we still have a bunch to finish on Monday, including the math of this. All right. So electrolysis in aqueous solutions. At the positive electrode, you'll have another choice. The choice is going to be whether the negative ion in the solution gets oxidized or whether OH minus gets oxidized. And here you get a summary of what happens. They tell you that the negative ion is simple, such as a monatomic anion, a single element anion like the halogens, then they will be produced at the positive electrode, which yes means if you were to electrolyze sodium chloride, aqueous in water, you would be producing at least a small amount of chlorine gas because it gets produced. So would we want to electrolyze salt and water? Probably not at a very high concentration. Maybe you could do it at a low concentration. Well, like I said, I will tell you why you could do it at a low concentration. And then here, if I have a polyatomic ion, your good old polyatomics, instead of them getting oxidized, what gets oxidized instead is the hydroxide in the solution. I'm going to show you how that happens on the next slide. So this is the concept that you have to remember. If I've got a negative ion, what's going to happen is if it's a single ion, it gets oxidized. And if it's a polyatomic ion, OH minus gets oxidized instead. So here we go. So what is the solution? Is that aqueous? Great. That means I'm creating everything from scratch here. Did not have time to make a Canva for this. So just writing it down. Hey, I was working till 9:30 p.m. last night. Jose kept texting him about the stuff for this today after school. Because every time something would come to mind, I'd be like, that's gotta get edited. I was still working on the stuff. So what is the solution? He's president, so he was like working on the presentation. You set it like at 9 p.m., right? Yeah. So what if we have a lot to go over after school today? What if the solution is aqueous? Here we go. Let's say that we had NaCl and water. And we applied electricity. Very basic. Right? We applied electricity to this. Would the sodium get reduced and become Na? Or would the H plus get reduced and become H2? Which one seems like it's the thing that's going to happen?
Sodium?
What?
The sodium?
Oh my gosh, really?
I mean,
We gotta test that. We're gonna have to test sodium.
oh, never mind.
What?
It's the hydrogen that gets sodium inside?
Yes, for sure. You make hydrogen gas.
What happens to the OH minus?
We'll talk about it. Yeah, that's gonna be important. It's the H plus that gets turned into H2 gas because really, are you going to make when this process happens, are you gonna make sodium solid in water? Is that something you think naturally happens?
No.
No, why not? Because if you were to create sodium in water, it would just give its electron back up. Immediately as you're trying to force the electron to it, it's like, no, stop trying to give that to, no! Don't give me that electron, right? Don't give me the other electron.
Sodium is reduced, it turns to solid, like the metal is reduced, it turns to solid, but the
Remind me to do some sodium in water when we do the experiment.
Question. What if we have
We can electrolyze it afterwards.
what if we had a supersaturated solution of sodium chloride?
It's still not gonna, you're still not gonna get the sodium out of it. It's not, it has to be molten. You would get chlorine gas in a sufficient amount to be dangerous. Okay, so the other situation, you've got Cl minus, it's got the option to become Cl2, or you've got OH minus has the option to become O2. What did they say is the one that happens? It's the fluorine. So that's why I said, so 1/2 plus E minus, this would actually be produced in this reaction. And you would be making small amounts of chlorine gas. If you were to take salt and you were to apply battery electricity to it, you would make small amounts of chlorine gas according to the concentration, dependent on the concentration. So that's situation 1. Situation 2, let's say we have copper sulfate. Cu plus 2, SO4 minus 2. I like to work with copper sulfate a lot in the class. It's easy, cheap to work with, and it's pretty. It's a blue solution. So
It's pretty blue crystals.
H plus, OH minus. Compare again. Copper or hydrogen? Which one do you think is going to get reduced? Copper or hydrogen? And once again, you'll be testing all of this experimentally in just a couple of weeks. The answer is copper. It's lower than hydrogen on the activity series. It will be produced. So you would not see hydrogen gas bubbling out of this one, out of the one electrode. And then for sulfate versus OH minus, which one would happen? Sulfate I don't even know what that would go to if it happened, but it doesn't. You don't have to predict what the polyatomic ions go to except OH minus.
Sulfur dioxide oxygen.
Maybe sulfur dioxide and maybe H2O, I'm thinking, like additional water produced, and then the SO2 gas would come out. That's possible. But it doesn't, actually. That's not what actually happens, aqueous. What happens is the OH minus gets turned into O2. Oh, wait. How? Where's the hydrogen?
The acid, the positive hydrogen.
Where's the hydrogen? Like here, we said, okay, hydrogen plus goes to H2, that's balanced, great.
Solution is aqueous, right? So
How would this be balanced? Remember last class?
plus H2O.
There has to be water, right? So there would have to be H2O and water, and we'd have to, from there, it's not acidic, so you wouldn't have to add the H plus. It's OH minus, actually. So you just have to make sure this is balanced. This, I would say, would need a 2 here. This would need a 1/2. That's balanced.
Gross.
But what else would we have to balance? We would have to balance the amount of electrons. So then -2 here, 0 here, so this is plus 2E minus. And so this would be the oxidation reaction for OH minus. And yes, you are expected to know that for this class, which is why I started teaching it last class. Okay, I think we have time maybe for one paper 4 question. Maybe. Go ahead, Issa. Okay, come back to it on Monday. Paper 4. Complete the table, identifying the substance liberated at each electrode during electrolysis with inert electrode. They didn't specify what the electrodes were made of. They're just telling you, hey, these don't react. Don't consider them. All right, so my electrolytes AgNO3. What would be happening at the anode? What would be happening at the cathode? What's your first thought process here? It's aqueous, right? So that means what's involved? Water. So for the first one, you've got Ag plus or H plus. Which one's going to be reduced out of these two? Silver. That's going to get reduced. Reduction is cathode or anode? Reduction, right? So what would happen? What's made here? The cation becomes silver. No longer cation, right? Because the whole point is it gains the electron and goes to Ag. That's the reduction. Okay, what about nitrate? Would it be nitrate or OH minus that gets oxidized? OH minus, because it's never the polyatomic ion, right? So what does OH minus become? O2. And that's an oxidation, so therefore O2 is being produced here.
Wait, where'd you get the OH minus from the NO3? From nitrate?
Aqueous.
Oh, right.
And if it's aqueous, that means you have everything there. You've got H plus, you've got OH minus, you've got Ag plus, and you've got NO3 minus, and basically you've got ions competing over what gets reduced and what gets oxidized. That's why it's a little bit more complicated. Concentrated NaCl. Would I make sodium, yes or no? No, I still make hydrogen. And then here I would actually make Cl2 gas. And then copper sulfate I just showed you, right?
Yes.
What are the products of copper sulfate? You would get the copper. And for sulfate, you would get the
Oh, wait, fine.
oxygen. OH minus would turn into oxygen gas. I think it is time that we stop. I think we have to stop here, unfortunately. So to be continued. To be continued. I told you this lesson was going to take a while. So we finished it on Monday.
Like I need to do that.
So the only homework due is the homework from lesson 1 on Monday. Yes.
I need to know.
You need to know?
I need to know. I need to know.
Okay,
Because
it's
I'm not.
molten. So that means no water. So it would be Ca+2 because it's calcium's in the second group,
Me too.
and it gains 2 electrons to become regular calcium.
So it doesn't matter if it's above hydrogen here.
Oh,
No,
that's
because there is no hydrogen. Because it's not
A, B, and C. Agree. Basically, it's like you don't really need it. I'm saying, oh, these are the sources that agree. These are the sources that.
Yes.
I have a question.
Go ahead.
Okay, so we can have a substitution, not single displacement.